Good morning everyone. I am here to demonstrate about the functions of moments. In functions of moments, there are two types: characteristic functions and moment generating function. Here, moment generating function is denoted as capital MGF. Definition for function of moments. To calculate the nth moment of a random variable x, two functions are generally used: characteristic function and moment generating function. Characteristic function: for a random variable x with probability density function fx of x, the expected value of e power j omega x is called the characteristic function. It is denoted with phi x of omega. Mathematically, it represented as phi x of omega equal to e of e power j omega x. Here omega is a real variable and j is the imaginary unit. For continuous random variable, phi x of omega equal to integral minus infinity to infinity e power j omega x fx of x dx. For discrete random variable, phi x of omega equal to sigma I equal to 1 to n e power j omega xi p of xi. Properties: the characteristic function transforms the random variable x into another real variable omega. It can be expressed as a Fourier transform of fx of x. Thus, fx of omega phi x of omega equals to fx of x or Fourier transform pairs. Inverse Fourier transform: the probability density function fx of x can be obtained back from phi x of omega using the inverse Fourier transform. Here the inverse Fourier transform formula is fx of omega fx of x is equals to 1 by 2 pi integral minus infinity to infinity phi x of omega into e power minus j omega x d omega. In this equation, phi x of omega equal to characteristic function of x. It is the Fourier transform of fx of x. Fx of x can be obtained as the inverse Fourier transform of phi x of omega. Here, phi x of omega and fx of x form a Fourier transform pair. Continue with the theorem. Moments from characteristic function. If phi x of omega is the characteristic function of a random variable x, then the nth moment of x is given by mn equal to minus j whole power n d power n phi x of omega by d omega n, where omega equal to 0. Characteristic function definition: for a random variable x, its characteristic function is phi x of omega equal to e of e power j omega x. By using the Taylor's theorem expansion, e power j omega x equal to 1 plus j omega x plus j omega x whole square by 2 factorial plus j omega x whole cube by 3 factorial and so up to so on j omega x whole power n by n factorial. Now applying the expectation on both sides, e of e power j omega x equal to E of 1 plus E of j omega x plus E of omega x whole square by 2 factorial up to so on. Phi x of omega equal to 1 plus here E of 1 equal to 1. E of j omega x equal to j omega into x plus j square omega square by 2 into E of x square plus j cube omega cube by 6 E of x cube and so on. Here phi x of omega equal to, here 1 equal to m naught and ex of x is equals to ex of x is equals to m1, e of x square equal to m2, e of x cube equal to m3, and apply those terms in the equation and differentiating on both sides with respect to omega. While differentiating, look into those terms clearly. D by d omega into phi x of omega equal to 0 plus j m1 minus omega m2 minus j omega square by 2 into m3 plus and so on. Here at omega equal to 0, d by d omega into phi x of omega equal to j m1. Here m1 equal to minus j into d by d omega into phi x of omega. d square by d omega square into phi x of omega equal to minus m2 by minus m2 minus j omega m3 plus and so on. d square by d omega square into phi x of omega equal to minus m2. Minus m2 equal to minus j whole square into d square by d omega into phi x of omega, where omega equal to 0. Compare the equation above terms of m1 and m2. mn equal to minus j whole power n d power n by d omega n into phi x of omega. Let us discuss about the characteristic function. Properties of the characteristic function. The characteristic function is unity at omega equal to 0 and given by phi x of omega equal to phi x of 0 equal to 1. The maximum amplitude of the characteristic equation is unity at omega equal to 0. That is, modulus of phi x of omega is less than or equal to phi x of 0, or phi x of omega is less than or equal to 1. Let us see the proof. Let the characteristic function phi x of omega is equals to e of e power j omega x. The amplitude of phi x of omega is modulus of phi x of omega equal to modulus of e into e power j omega x equal to minus modulus of integral minus infinity into infinity fx of x e power j omega x into dx. Since modulus of e power j omega x equal to 1, therefore modulus of phi x of omega is less than or equal to 1. The third property is phi x of omega is a continuous function of omega in the range minus infinity less than omega less than infinity. Here omega is the continuous, e power j omega x is also continuous. Hence, phi x of omega is a continuous. Let us see about the fourth property. Phi x of minus omega and phi x of omega are conjugate functions. That is, phi x of minus omega equal to phi x into omega 5x into minus omega equal to 5x of omega. Let us discuss about the moment generating function. The moment generating function mgf of a random variable is also used to generate the nth moment about the origin. Consider a random variable x with a probability density function fx of x. Then the moment generating function of x is defined as the expected value of the function e power v into x. It can be expressed as mx of v equal to e into e power vx of x, where v is the real variable and its limits is minus infinity less than v less than infinity. Therefore, mx of v equal to minus infinity to infinity e power vx fx of x dx. For the discrete random variable x, mx of v equal to sigma n equal to 1 to n e power v into xi into p into xi. Theorem for the moment generating function. If mx of v is a moment generating function of a random variable x, then the nth moment of x is given by mn equal to d power n mx of v by d into v power n, where v is equal to 0. Consider a random variable x with moment generating function mx of v equal to e into e power vx. We know that the Taylor's theorem expansion. Apply the Taylor's theorem expansion. E power vx equal to 1 plus v into x plus vx whole square by 2 factorial plus vx whole cube by 3 factorial. Applying expectation on both sides. E into e power vx equal to mx of v equal to e into 1 plus e into vx plus e into vx whole square by 2 factorial. We know that the m0 equal to 1, m2 equal to e into x square, m1 equal to e of x, m3 equal to e of x cube. Differentiating on both sides. d by dv into mx of omega equal to 0 plus m1 into v into m2 plus v square by 2 into m3. Here m1 equal to d by dv into mx of v, where v equal to 0. m2 plus v into m3 equal to d square by dv square into mx of v, where v equal to 0. The nth moment of generating function is mn equal to d power n into mx of v by dv power n. Let us see about the properties of the moment generating function. The moment generating function at v equal to 0 is unity. It is given as mx of v equal to 1. Let x be a random variable with moment generating function mx of v. Then moment generating function for y equal to ax plus b is given by my into v equal to e power v into mx into av. If mx of v is a moment generating function of a random variable x, then mx into cv equal to mcx into v, where c is a real constant. Let us do the one example. Let x be a random variable with PDF fx of x equal to 1 by u into x e power minus x by 2. Let g of x equal to x cube. Find e of g of x equal to e into x cube, and apply the definition e of x cube integral minus infinity to x cube fx of x dx, and do the same steps like that and multiply the prefactor. E of x cube equal to 1 by 2 into 96 into equal to 48. E of x cube equal to 48. 48 equal to 48. By using the gamma integral formula, we can do this problem. Thank you for giving this great opportunity.